Hi everyone, so we're going to be looking at the bonding triangle in a little bit more detail. So from what we've learned so far, we've seen that bonding is either ionic, covalent or metallic, but we're going to see that some materials cannot be categorized easily as metallic, ionic or covalent. Actually, bonding is more as a continuum between ionic, covalent and metallic models. So to represent this, we use the bonding triangle, and the bonding triangle is given in the data booklet. So in the data booklet, it looks like this. This is what you will find. And at the three peaks of the triangle, you will have the nature of the bonding. So at the top, it's strongly ionic. Here, it's strongly metallic. And here, it's strongly covalent. And the location of an element or a compound in the bonding triangle will help us know what type of bonding is present in that substance. And this is determined by electronegativity values of the elements in the compound or in that substance. So in the bonding triangle, you have two axes, as you can see here. You have on the y-axis, you have electronegativity difference. So electronegativity is represented by chi, like this. And electronegativity difference is found by subtracting the electronegativity values of the elements in the compound. And here we're going to take the modulus. So whatever value you have for electronegativity difference, you take it as positive. So for example, if I have F2, the two elements present in F2 would be F and F. So electronegativity difference would be 4 minus 4, which is 0. If I have NaCl, for example, difference in electronegativity would be electronegativity for Na. I'm going to look it up in the data booklet. So you have Na here, 0.9, Cl is 3.2, which is minus 2.3, and we're going to take the modulus of this, which means that we're going to have only the positive value. So this is the difference in electronegativity. So this is the y-axis. So by having the value, you can position on the y-axis. So you have a scale here. So you can position where the substance is found on the scale. So 2.3 is going to be around here, and 0 is going to be here. So depending on the value, you can position it. The x-axis is the average electronegativity. This is the sum of electronegativities divided by 2. So for example, for F2, you will have 4 plus 4 divided by 2, which is 4. And for NaCl, you're going to have 0.9 plus 3.2 divided by 2. So for F2, the average electronegativity is 4. So it's here. So on the x-axis, it's 4, and on the y-axis, it's 0. So F2 can be positioned here. And if you look for NaCl, on the y-axis, NaCl is 2.3, and on the x-axis is around 2. So NaCl is positioned here. So using the x-axis and the y-axis like this, you can position different substances, and from this we find that NaCl is in the ionic region and F2 is in the covalent region. So if you find something that's in this region, it will be polar covalent. If you find something in this region here, this is going to be metallic. So similarly, you're going to Out the average electronegativity and the electronegativity differences for all these substances and find the position in the triangle. I'm going to do for one of them so that you have an example. Let me take for CF4. So the bonding is between C and F. So the first thing, I will find the electronegativity of carbon in the data booklet. So section 9 of the data booklet. Carbon is 2.6 and fluorine is 4.0. Average electronegativities, this is the x-axis. So it is 4.0 plus 2.6 divided by 2. And the electronegativity difference, this is 2.6 minus 4.0. You can do 4.0 minus 2.6. I'm just pointing out that whatever value you get, you're going to take the modulus of it. So it has to be positive. So difference is 1.4. So on the x-axis, CF4 is going to be 3.3, so in that area. And the y-axis is going to be 1.4. So I've subdivided a little bit the axis so I can get it more accurately. So I find that CF4 is in this region. So it is in the region of polar covalent. So this is polar covalent. So for each of these substances, you will find the position on the x-axis and the position of the y-axis to deduce the position of that substance in the triangle so that you know what type of bonding that is. Pause the video, work it out for all of it, and then you replay the video to check your answers. So verify your answers. And I have used my bonding triangle. You will see here, like I have found the positions of each of these compounds as accurately as possible, and I have used little graduations when the values are in between. So I match the x-axis and the y-axis. So for example, if I do for lithium oxide, so there's LiNO, so 2.2 on the x-axis, 2.4 on the y-axis. So 2.2 here and 2.4 here, so I know that it's here. And you will see that the stoichiometric ratio has nothing to do in the calculation because the bond is only going to be between Li and O. So it's only the interaction between two atoms that we're looking at. So whether it is Li2O, so there's nothing to multiply with these two. So we're only looking at two elements, and the position of the compound or substance in the triangle is noted over here. Now you can also use the bonding triangle to assess percentage ionic or covalent character. So I will do one example. I will do for magnesium iodide. So I will use the section 9. So magnesium is 1.3, iodine is 2.7. So you see the electronegativity values are at the bottom. So I have 2 and 4 here. I will look it up in the bonding triangle. So you can see that magnesium iodide is here. So 2 on the x-axis and 1.4 on the y-axis. So this is going to be in the ionic region. And if you look at here, you have percentage covalent character. So it's going from 8 to 25 to 50. So between 50 and 75. So you can say maybe it is around 60 here. And between 50 to 25, you can say maybe 38 or 40. So magnesium iodide is actually going to be 60% covalent and 40% ionic. And be careful when you add these two percentages. Of course, it should give you 100%. But you can already see magnesium iodide. Normally, you would expect it to be ionic. But when you find it on the bonding triangle, you see it is 60% covalent, but 40% ionic. So similarly, work out for these two substances and then you check your answer. So pause the video now and work it out. Now from this, we see that aluminum chloride here exhibits both ionic and covalent character. Aluminum chloride has an unusually low melting point, even though it appears in the same region as magnesium iodide. This tells us that the bonding triangle cannot always be used to predict properties of a substance, especially if that substance has mixed character, just like in the case of aluminum oxide, but there's 50-50%. And aluminum chloride is right in the boundary, so as you can see 50-50, which means that it exhibits both covalent and ionic properties. So you can see the bonding character of all these substances. So I've color coded it. If you want, you can pause here and to see where I looked for the different compounds and how I use the ratios of percentage covalent and ionic. So aluminum chloride forms ionic lattices when solid, but at high pressure the ionic lattice will melt and it's going to form aluminum chloride dimers. And this is how the dimer looks like, and in the dimer you're going to have coordination bonding. So you can see that the chlorine donates both electrons to aluminum here and here. So this is Al2Cl6, and it forms this type of dimer when aluminum chloride melts, and this melting occurs, so melting point occurs at 190 degrees Celsius, which is extremely low for an ionic compound. And also, unlike ionic compounds, aluminum chloride, this is soluble in non-polar solvents. Normally, ionic compounds should be soluble in polar solvents. So aluminum chloride is actually soluble in non-polar solvents like tetrachloromethane. So depending on the type of bonding, the property is going to be different. So we've already seen properties of each of these substances. So then you can relate bonding type to property of the substances. You can read about alloys, and you should be able to understand that alloys are a mixture of metals and other metals or non-metals, and that alloys have enhanced properties in comparison to pure metals. And you should be able to explain the properties of alloys in terms of structure. So make sure you read this, especially concerning the non-directional nature of metallic bonds, and you go through this table. Remember, for brass, bronze, and stainless steel, brass is easy to remember, so it starts with B, and there's an S here. So one trick I use to remember is that B leads to C and S leads to Z, so it's copper and zinc. And stainless steel, you will know that it comes from iron, so it comes from steel, so there's iron in it, and then we add chromium, nickel, and carbon. And bronze is copper and tin. B leads to C, copper, and Z here actually leads to S, which is tin. Sn is the symbol for tin. So that's how I remember the elements present for these three substances. To finish this, make sure you complete the homework assigned in this topic. The next video will be correction of those homework.